Okay. So, I would like to start rehearsing what we did last time and also saying a few words about the current exercise 6, that I just distributed to you. So, what we did until now is we introduced optimal control problems and brought them into the form of general nonlinear programming problems. So, we actually used the language of optimization. And we realized that there's different formulations, namely the sequential approach and the simultaneous approach, which are very related but different. And the aim of this exercise is to investigate that relation and to learn about both of them. What are the implications on the sparsity structure of the Newton type optimization method? Okay? So this is an exercise that's completely related to what we did last time. What I maybe should say about this, we ask you to address a very interesting or very simple optimal control problem, namely the one of a pendulum that's swinging up. So we have a pendulum which has an angle phi, and you can apply a torque that we call U here, not T, but that is the control basically. And of course there is some dynamics, so this usually would fall down. But with this torque you can actually actuate it, you can actually also make it oscillate. And we want to start with a hanging position and we want to move it up with minimal effort of torque. Actually the objective is a mix of state penalties, so all penalties are deviation of the pendulum from the top and the square of the u's, but if you start here, you need to have some controls in order to make it swing up and move to the top. So that's the problem we want to solve. I think we don't need questions about this exercise sheet at the moment. If you have, you can ask them in the break. And this is everything I wanted to say about the exercise sheet. The exercise will take place tomorrow as usual, but the tutor will be Dimitris Kouzoupis tomorrow because Andrea Zanelli is on a summer school in Zurich for his PhD program. Okay. What we want to do today is actually looking at, of course, the whole lecture we look at optimal control problems, but we look at them from a very different perspective now. So today I want to present you an approach to optimal control that is not related to nonlinear programming or not so much connected to the rest of the optimization world, but is completely specific to optimal control. But at the end you will see that it's all very connected. So today we talk about dynamic programming. And dynamic programming is something many of you might have heard about, some of you maybe not. It's something that's also popular in computer science and usually taught there. But we will present it from our perspective of optimal control. So this will very often be abbreviated DP, and because there are so many variants of dynamic programming, there exists also a variety of abbreviations which all have the DP somewhere in the title. So who has ever heard about dynamic programming in some lecture? The keyword dynamic programming. Okay, some, yes, I'm happy to see, and not everyone is making me also happy. So dynamic programming is something that goes back to a person, the name at least, who introduced this word. And also many of the ideas is Richard Bellman, who not only invented it, but then also applied it in a lot of applications and made it really fly. And he influenced a generation or two of optimal control researchers and mathematicians in general. So the setup in which I want to present it is relatively close to what we did until now, but with a little difference. So I will present dynamic programming in discrete time and also in discrete state space. And that's actually where it is originally developed for, or where it's easiest to explain. And so what we will regard as a dynamic system, which we will write down as we did it before. So I just say what we need is the state. The next state is a map, is the old state and the control. Yeah? But I will now not specify the spaces. I will just say that the xk's, they are element in some space which I call x, and the uk's are element in some space that I call u, yeah, with a curly u. And the implicit assumption is that these are actually countable sets. Yeah? I don't specify them, so they could be Rn like usual, and also the formulas will still be valid, but if you really think of how to implement it, you should think of them to be countable. But sometime we will assume them to be countable. Countable sets, sorry, not only countable, finite. Yeah, so really finite sets. And then we would give them numbers, and I think I would use the numbers nx, so that's nu, yeah, elements. So this is the number of elements in each of these two sets. Nx and nu. Yeah, so imagine an automaton which would just have a state machine that is in some state, like it has the number 15 and this has the number 450, and together that maps to number 386, yeah? Something like this. Of course, this could be achieved by discretizing a state space or by other means. In chess, for example, you would directly have it. I mean, chess games are discrete by nature, and you could just give a number to every possible position in your game. Okay, so that's our dynamic system. It looks the same, but we keep in mind that these might be finite sets now. And now the optimization problem we want to solve is still the same that we wanted to solve before. So we want to minimize an objective function, which is the sum of some functions L, x, k, uk, k going from 0 to n minus 1, and a terminal cost, xn. And we have constraints which just say that xk plus 1, and yeah, let's write it like we did it before, xk uk minus xk plus 1 is equal to 0. This constraint should hold from 0 to n minus 1. And we also have an initial value that's fixed, x0 bar minus x0 equals 0. And our optimization variables are x0, u0, and so on in these spaces. And I will omit everything that is related to constraints, in particular inequality constraints, because I will allow the extension of these functions to infinity. So if a point is infeasible, I will just denote it by saying, okay, then this function L at that pair that is infeasible will become infinity. Infinity being the worst thing when you want to minimize is the obvious choice for an infeasible point. Yeah? So L and E map to R unified with infinity. And sometimes we give this a name. We give this the name R infinity. Okay? To mark infeasible points. So that's just to get rid of them, because it will make the notation much more tedious, and it's also in the implementation of dynamic programming, that is the way to deal with inequality constraints there. So we just assume that this function L is the cost, and if it's infinity, it means it's infeasible, and you should probably not visit that pair. And if the result of the optimization problem is infinity, so if there's no feasible point, then it's actually infeasible. Okay? So that's the setup now, and if I want to draw it, I could actually say here are my finitely many states at every stage. Yeah? And from each state, I have some possible transitions. Yeah? So there's many possibilities, right, that I can choose. And at every time point, I have to choose a control. The initial value is fixed. So if you think of it from a combinatorial perspective, how many possibilities do I have? In a way of sequential thinking. Imagine you eliminate your system dynamics. You can evaluate your cost. It will only be a function of your controls. So the vector of all controls will have how many possibilities? You will have n stages, right? N stages. And on each of them you have n u decisions to take. So these are the decisions. The initial value is fixed, I should say, so there is no choice here. So that's x0 bar, for example. But if you have n use decisions and on n stages, then it's a combinatorial easy calculation that the possible number of choices is nu to the power of n. So this is all the combinations of controls that you can choose, right? Possible choices. So this is like the stupid way to look at this problem, right? So you would just say, if I have this discrete automaton, each control has, let's say, 3 choices, and I have 10 time points, and it's 3 to the 10 possible trajectories of controls that I need to test, and I want to find the best of all these. Yeah? That would be not dynamic programming, but that would be what it can do better. So the idea of dynamic programming is now to enumerate all choices in a different way. So you will be sure that you have found every possibility and enumerate all possibilities differently. Yeah. I don't say more efficiently because it can be in some cases not as efficient, but it's you will see the difference. So the idea here, I mean, that's just the rough idea, but the concrete idea is that what dynamic programming does, it will assign to each of these states that you can visit, it will assign a cost to go. And the cost to go is the thing that you get when from this initial value, for example, I would go to the end with the optimal decisions from that moment on. Yeah? Of course, that's a very hypothetical concept because I need to know what are the optimal decisions from that moment on. But if I would know them, I could assign to this state here at this time point a certain cost, and that's the optimal cost to go to the end. So let's just introduce it and then see how this will allow us to easier enumerate all possibilities. So introduce something. The optimal cost to go. Cost to go. And we call it jk of x. And we define it actually as follows. We define it as the solution of an optimization problem on a short horizon, which is not starting at 0, but some index in between. Maybe I give it here already some bar here, for example. And I define it now like this. Jk of x bar is defined to be the sum. And now please note the index, and I maybe shouldn't use the k here. That's a bit nasty. Yeah, now I changed the index there. I used k. I will use I now, right? Just to make... So I will start at k, and my running index is called I now. I should have done it before, but that doesn't matter. So I will now define a shorter horizon problem, which starts already at index k. Yes, maybe I should say for k from 0 to n minus 1, including even n. We can define it even for n. I will see, you will see it in a minute. So, sorry, this is not the complete statement. I need to create extra space. So jk of x bar is defined to be the minimizer of this problem, which of course starts at x, k, uk, and so on. And it has only the constraints on the remaining horizon, so it actually says that f of xi and ui minus xi plus 1 is equal to 0 for I from k to n minus 1. And the initial value, which is actually x bar here, yeah, should be equal to xk. So k is now the first, so this would be index k. That could be the x bar. And it's a matter of taste if I want to give this an index or not. Here I decide to have it not with an index. Okay, in the script we have it with an index, so I do it with an index. But it's a fixed quantity, it's not a variable of the optimization problem. The variables are all the remaining variables from this moment on. Okay, so that's the definition of the cost to go. There is nothing gained, and you just say, hey, how can I solve this problem now? Does it help me? And it does help us, because if you would know this cost to go here, and you are faced with a decision to decide from any state where you are here now, what would be the optimal action for the future, you would just look all your n new possibilities, and from those you compute the cost that the stage, this one stage, plus the cost to go gives, because then you know that will be the optimal, and you choose the best of them, because that will give you the optimal way. The optimal next action will just depend if you know the optimal cost to go after one time step. It will help you very easily to decide what is your next time step. So let me just say, for example, if you play chess here, and someone magically tells you on this position you would win, on this you would lose, on this you will win, you would lose, right? So there's actually 0 or 1s. And then you just have your possibilities. I could do this, and then at some point someone tells you if you do this, then you will win. Then you would just do that, right? And there's no further discussion. You have to believe, of course, that this was really the optimal cost to go, and there's not an error. But once you trust the cost to go, it helps you a lot. Yeah. And I will tell you what's now the defining equation. So we call it the principle of optimality, and maybe we discuss it a bit. So this principle of optimality will just say that the cost, if you know the cost to go at the next time point, jk plus 1, and I will not specify yet at which argument, that it helps you to actually define the cost to go at the current time step. And so how does it do so? Let me just use this definition. Yeah? But then say, okay, I could actually just summarize everything that comes at the end with this same expression again. So I could actually minimize, here I have xk plus 1 and uk plus 1 and so on as variables. So I could actually separate this minimization into the minimization of the first two variables and then the rest. And by doing so, I would just minimize only over, actually only the first control, minimize u, yeah? And I directly eliminate that constraint, so I plug that into the function f. I plug it also into this cost, L will just be x bar k, that's not an optimization variable, and the u that I don't know, and I add to it the cost to go, which will be evaluated at the state where I would be if I choose a certain u. So that is the f evaluated at the same point as the L. So I will actually have the stage, the transition cost, so to say, plus the cost to go from that moment on if I would move to a certain point. And this identity is something which is, so to say, yeah, it's a tautology. Actually, it's just meaning I minimize separately over the first two variables, and okay, I eliminate that initial one for making it even easier, and then I minimize over all the remaining variables, right? So it's actually just a separation of the minimizations. But if you look at it, it just means that if I would know the cost to go at this stage, I need to minimize only over the controls, and then I know the cost to go at this stage. So this is what we call the principle of optimality, and I hope that you find it intuitive, but I can also try to discuss a bit about it and what it, so to say, means roughly. I mean, the principle of optimality, if you have here k and k plus 1, and then here the end, n. Yeah, so I draw it as if it would be continuous time, but of course it's discrete time. So imagine you would be at the optimal trajectory starting at this point. Yeah? So if you now restrict your optimization to an optimization problem from this point where you arrive in your optimal trajectory after one time step, and there would be a better trajectory leading to the end, then that was not an optimal solution what you had at the beginning, because if this whole thing was an optimal trajectory, and then someone else says, yeah, but from this point there's a better way, then you could say, okay, then this was not optimal, because then I would just go from here to there and then I get a better cost altogether, right? Because if this cost would be better than that one, then this was not an optimal trajectory. So the principle of optimality in different variants, you could also call it any subarc of an optimal solution is optimal. But it's an optimal solution is also optimal. That's what we exploit. So this is a subarc, the end, and that must be optimal if the whole thing is optimal. Okay, very intuitive actually. And this is culminating in this equation, and that is a recursion. We can interpret it as a recursion, because now what we could do, and that's the dynamic programming algorithm, it would actually start at the end and then compute this cost to go step by step in order to see what's the cost to go. And then we know more about the dynamics and of the optimality, and we can actually use it to make our decisions, and we will see that it's more efficient. So we have the DP a backwards recursion. That's the first part. By the way, there is, of course, there's backwards again, like in the reverse mode of dynamic algorithmic differentiation. But there is no direct relation. I mean, you can always find some, but not directly here. So the DP backwards recursion is actually the following. You start with what? You start with the terminal cost. The terminal cost is actually this thing alone. So you will just say, I have Jn of x defined to be E of x. So you have actually the terminal cost to go is trivial. It's just the cost to go at the end. That's this function. So then you go recursively or iteratively, as you like, for k starting at n minus 1 down to k equals 0. Actually, you could stop already at k equal 1, but for aesthetic reasons, I go down to the end. So what you do is, and then you apply this formula. I call it maybe, how do we call it here in the script? So let's give it the right name, 8.2. So use 8.2 to compute. So what will we compute? Jk of x, yeah? Or jk. I mean, here this is for all x in the state space, right? And here it's also for all x in the state space. So we need to actually compute it for every state in the state space. And then we end, but then we have the cost to goes. And at the end, we will do a forward recursion, because once we know the cost to go here, 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 then if we are at this point, we can use the cost to go to find the optimal action. So there will be followed by this. So the result of this thing is J0, J1 up to Jn functions. So these are all functions basically from states. If it's a finite number of states, then these are basically vectors. Yeah? It's just a collection of numbers, the cost for every state. So, but then there is a DP forward recursion. Could also call it a sweep. And this DP forward recursion will just get the optimal solution. Yeah, so get optimal action. Yeah, by the way, action is the way that computer scientists call a control. Yeah? So we could also call it get the optimal action. Control. From this, you just say the optimal control at a stage k. We know it. It will be one of the minimizers of this function. Yeah? So it's actually possibly not unique. So I better write something like element of the argument that minimizes from all u this cost function here that we had, xk u plus jk plus 1 xk, f of xk and u. So that's the same expression, just that now we are interested in the value that minimizes it. And simulate the system. For k 0 up to n minus 1, using now the following, we just say xk plus 1 is equal to f of xk, and we apply the optimal feedback here. Yeah. And of course we start at which value do we start? At x0 equals x0 bar. So we actually, after we have computed all these cost to goes, we would just take our value x0, then we are here. Then we take a decision, okay, which of our possible controls will give us the best value? That one we choose. Then we are here, for example. Then from this moment we will also take our optimal decision, which of the optimal controls gives us the best point. So that's the easy part. You just go forward. Yeah? And maybe I should call that this whole thing, this definition that we have here, is the optimal feedback control. Why do I say feedback? Because it's actually very much like a feedback. When we would have a different state, we would get a different control here. So it's not just some value. It's actually this is a law. Because for any x, it would give us a different control. So this is now the forward sweep. And together, this is a way to solve the optimization problem. And let us think about what cost will it have. Yeah, so here we would have so many choices. Okay, I discussed it already, but what is the cost here and how many things do we need to enumerate if this would be finite? So the cost of the backward sweep, costs of backward, or TP, yeah, so this recursion. So what will it be? I mean, it will be, you will have to store, I mean, you will have to initialize all these values that we say is no cost, right? So every single state, you will have to copy basically that to this new value. So that's not no work. But then you will have n steps, and in each step, you need to, let's say we are at such a point, we need to evaluate the system dynamics once. Now, let's assume the system dynamics is expensive, right? And also the control, for each control. So we will have to do n times, big N. We need to go through all states, which is little nx. And for each state, we need to explore all possible controls n u. So this would be the number of calls of the system simulation, this f and l. So many calls of L and F, in order to get all these cost to goes. And then in the forward sweep, what would we need? I mean, there we just need to call this f n times, and of course we could have stored these values even, so we could actually have stored them. So I will not have cost here, and here it's just n calls of f. So that's trivial, it's not another order of magnitude, I mean it's just n times, okay. This is usually something like thousands or millions, right? So we don't care about this forward sweep. So I just say forward sweep is negligible. But this is the main point. So how many calls of f would we have needed in this scenario? I mean, for each choice, we would just fix the first control is at 1, the next one is at 3, this next one is at 5, and so on. For every choice, you would, in a naive implementation, just simulate the whole system. So you wouldn't need to do all the n simulation steps even. So you would need n times this possible choices. So please compare it with n times n u to the power of n. So these two are the costs. This is dynamic programming, this is the naive approach. So for the naive approach, you see that the n appears in the exponent, the big N. So for longer time horizons, it's definitely not competitive. What you also see is that there's no state dimension appearing here, but there is a state dimension appearing here. So that's a difference. Yeah? Linearity in this n is present in both. So basically you need to compare this number with that number, and that very quickly, usually, I mean, this is getting smaller once your time horizon is slightly longer than a few time steps. So you see that it's really a much more efficient way to enumerate all possibilities. Yeah? So please keep in mind, dp enumerates or checks actually, right? All possibilities. So there's nothing about global or local optimization. I mean, it's the global solution. So it finds the global solution. Global minimum. So that's like one of the first nice features. The second really nice feature, I think, is also very worth to think about, is it delivers not only just one trajectory, but it delivers even a feedback control law. So if you would, the next, so someone says, please solve that problem, and then you have solved it with dp, and then the same person says, okay, by the way, the initial value is changed now. Can you solve that problem again? And you say, yeah, and you have your solution. Yeah, because you have, if you have the storage of your cost to go function, you can very quickly get back the forward solution by forward sweep. It computes a feedback control law, yeah? a feedback law, basically. So it's not just one open loop, not only one trajectory. So that can sometimes be very useful. So both these things can be useful. But there must be a drawback. So why did I teach you all the rest if this is like such a nice method? So the drawback is that usually these sets are not finite. Yeah, I mean, when we are in Rn, what can we do? And what you will have to do if you're in Rn, you would have to discretize your state space somehow. And that means really make a grid. And if you have a two-dimensional state space, yeah, so maybe I just say it, need to discretize state and control space in most applications. So if you're lucky and you are playing chess or some computer games, you might be working in discrete state spaces, but if you're in Rn, then you have a problem, right? And so now let me just say what we do. So you have Rn, Rnx. Yeah? So what is Rnx? It's okay, an nx dimensional vector space. And now you would just discretize it with, let's say, 100 grid points in each direction. Yeah. And I think I gave it a name, so I should just use the same name. M. So grid points in each dimension. So let's visualize it here. You would have a two-dimensional space, right? You could say, okay, maybe I have some box in which I will be with my state anyway, maybe some upper bounds and lower bounds of controls, right? And then you need still to make a choice. And you will actually discretize it in typically rectangular grids, right? So that would be one way. And if I have now m in each dimension, just to make it simple, then I need m to the power of nx states. And each of these grid points would be then one of the possible states. So then you would get nx equal to m to the power of nx. Yeah? You agree? That would be the number of possible state points. And this is, again, an exponential growth in something different, namely in the dimension of the state space. And so this is something that also Bellman observed already. I mean, it's like the main problem of dynamic programming. And it's commonly, T already called it that way. He said that's the curse of dimensionality. I mean, it's appearing in many parts of science, but here again. So it's not a cure for everything. And if your state space is, for example, 10-dimensional, which we easily have in simple sets, right? 10-dimensional, and you have 100 grid points, then it's 100 to the power of 10. That's 10 to the power of 20. So it's a 1 with 20 zeros possible states. It's very difficult to store that amount of data even. Yeah? So you see that this is getting very quickly out of reach for anything that you can compute, unfortunately. Yeah, otherwise, optimal control would be solved already 50 years ago, 60. Okay, so this was the idea of dynamic programming, and I think I would like to give some time to digest it, because we will build on that idea, and I've presented everything you need, so to say, to in principle, to implement it, but it was relatively fast, possibly. So first of all, I would like to invite you for questions. Or is there some step on the blackboard that you would like me to discuss a bit more? Or maybe there are also errors on the blackboard at the moment. Should I maybe just go through the story again to make it a bit, to see if there are some questions on the way? Is that helping? Yeah, because I still want to be sure. So what we did is we have an optimization problem, optimal control problem, and we break it into, so to say, shorter horizon problems. We define the cost to go, the optimal cost to go, and then we defined a relation that the cost to go needs to satisfy, namely the cost to go at 2 consecutive time points is related to each other via this simple formula here. And this formula is the key for the backward recursion, what we described here. So you start actually the cost to go at the very end of your horizon. I mean, at the very end, you know what is your cost to go, because when you're at the end, you will just have the terminal cost. Yeah? There is nothing to do. But then, for going one time step back, you will actually, for each of these states, you will compute what is the cost of the step plus the terminal cost, and when is it minimized, and the minimal value I put as a number in this location of the vector here. So I will actually just have nx numbers as the result of each of these dp backward steps. And then if I have these nx numbers, I can just go to this time step, and I also, for each state, I evaluate the different possibilities, and I remember the best result, and that's what I put into this memory location. And so I fill all these memory locations here, assigning to each state the cost to go of this state to the end. And once I have done that, I will use this knowledge for a forward sweep, and that solves me the problem. And if I want to solve another problem with different initial value, I could very quickly do that with another forward sweep because I have all these costs to go. So the key is this recursion, and that recursion is, I think very, it's trivially true, so to say. But this is like the key. If you find that not logical, then of course you will doubt that DP works. But I hope you find it logical, and if not, please help me to convince you. So who finds this principle of optimality or the dynamic programming recursion, who finds that now intuitive, this thing? Who finds it intuitive? I find it intuitive, but okay, you don't have to raise your hand. Are there questions regarding this principle of optimality? Yeah?
Is it still used in practice, or is it just to teach the fundamentals?
Dynamic programming.
Practical application?
Yeah, reinforcement learning builds on that basically. So it's in that sense you could say it's all used in practice. There are many special cases which are definitely used in practice, and one of them I will present after the break. But yeah, it is used. I mean, usually maybe I should say when you use it in practice, either you grid your state space and then you are two-dimensional. 2 state dimensions is okay, like this one. 3, 4 sometimes, but it's getting difficult. And what people do otherwise is they represent the cost to go with something which is not enumerating everything, but for example, there's a field of neurodynamic programming where they just represent it with some neural networks or such things. Yeah? So you can actually try to approximate the cost to go functions differently than just by gridding. Yes?
If we use this, this
DP
principle, this DP in forward recursion, wouldn't our algorithm be greedy, as computer scientists say? So
yes.
We start at the beginning and then we just take the easiest path.
Exactly. So that's the nice thing. It's actually like a greedy algorithm for the forward recursion, but because you have the cost to go, it is greedy with a perfect view on the future. Because it knows already that after one time step, if I arrive at that state, then I have already a plan to the end, which will give me that cost. So in that sense, it's greedy, but it's not greedy because it knows already the future. But it's as easy to implement as a greedy algorithm. Yeah. So maybe I should also give you some simple applications. Actually, there is an algorithm that's called Dijkstra's algorithm that's for finding shortest paths. That's actually dynamic programming. So if you want, I mean, you have a big network of many streets. Actually, you use it probably all the time. You just Google directions. You say, I'm here, I want to go there. Find the shortest path. How does it do it? It will, I mean, there's every crossing, there's 2 possibilities at least, right? And how many crossings do we have in Freiburg? Let's say 200. So 2 to the 200 possibilities, that's not all explored. So why does this algorithm just instantaneously show you the shortest path? It is because it uses dynamic programming, and it does so by just, for example, it starts at the end or at the start, you can choose. Huh? Let's say at the end location, that's more useful because when you're driving, you sometimes don't do what the algorithm says, right? So starting at the end, it can just compute the length in minutes that every path would take. So you start somewhere, this is where you want to go. And then you look at neighboring points and you think, give to each of them, so to say, a score, which is how long does it take you to go to the end in minutes or in seconds. And then you enlarge it by the next round of neighbors, and there you assign a value to each of them. It's of course slightly different because this is not, I mean, the time stages are slightly different here, but it's the same principle. I mean, you compute the cost to go to the end, and then it will very easily, you just have to visit every state once in this algorithm. Yeah? So it's a relatively, it's cheap. That's called Dijkstra's algorithm. So that is used every day, very often. I should say that also for optimal control, sometimes people use it. I know some people that drove trains in Switzerland with it, that just had to, what did they want to minimize? I think they wanted to minimize the electric energy consumption, and they wanted to arrive exactly in time at some station. Yeah. So when you go upwards and downwards and so on, so it can be involved, and you also have switching and so on. But the state space is a simple one dimension in that case. It was just, I think, the velocity that you had at every meter of the train. So there are people that use dynamic programming. Also for battery charging, I've seen people using dynamic programming. There, the state of charge of the battery is one state, it's one dimension, so it's a beautiful, simple thing. So usually 1 or 2 dimensional problems use dynamic programming. And then the rest is, it's an important concept to keep in mind. And we will actually dig in this chapter a bit more into it. Okay, if there are no more questions on there's one more, yes?
So when we want to compute an optimal control problem, the first step would be to do this backward recursion, and then we do this forward recursion.
Exactly. So in dynamic programming, you first do the backward and then the forward recursion. I should say that, of course, there is, because, I mean, if you think of it from an algorithmic point of view, you could also do it the other way around. You could also compute the cost to arrive, and then you just reverse time. So also this variant would exist. Yeah.
Okay, so it's like setting the end point to the start point.
Yes, exactly. Yeah, so yeah, slightly different because the system dynamics is still defined in forward, but you could basically reverse engineer the algorithm. There's also other variants like dynamic programming on trees. So you can do it on trees. So there are many different possibilities, and they can be very exciting. Yeah?
Isn't the backward propagation not just basically building a tree?
No, it's not building a tree, actually. Yeah, you could say so. If you think so, it's like the tree of the optimal solutions. Yeah, it's an intelligent way to enumerate the tree of possibilities. Yeah, that one is one way to look at it. Mm-hmm. Actually, maybe I should say that if you think of it, if you compare these costs of simple enumeration, which would just be a tree of all possibilities, with the dynamic programming, you see the state dimension enters, and dynamic programming uses the fact that it's not just, so to say, a tree of possibilities, but that the bottleneck, the memory from one time point to the next, is via the state. So everything that you know about the future is summarized in the state. So that's what makes a system, right? So the state is the only memory that you have that tells you something about where it will develop in the future. So this is exploited in dynamic programming. So without a state, there would be no dynamic programming. Okay, so if there are no more remarks, then we had just a very quick hour on dynamic programming, and afterwards we will apply, so keep this formula in mind, because we will apply that in specific contexts now. But first we do a break, like 10 minutes break, and 1:15 we see again. Okay, so there was a short question about the exam. So if I know already when it will take place, I think it's not yet absolutely fixed, because we offered some dates to the exam office of the Faculty of Engineering. These dates that I offered were 21st and 22nd of September. So it might be one of these 2 dates. Okay, there was another question.
Can we still or already apply for the project?
Yes, we can help you if you need. I would recommend everyone to do the project. It's relatively synergetic with the lecture, let's say. Yeah, very synergetic.
But it wasn't in the system.
Sorry?
Like last week, it wasn't in the system. The project, it was only under the study for sustainable energy.
What? Only under what?
Only for the field of sustainable energy. Something.
Okay, so can you, because I will certainly forget it. So this is an error. It should be available to ESE and MST students as well. So can you try to ask them to correct it in the Prüfungsamt? in my, so one of you should just get the task. Can you go to the Prüfungsamt? Or you, Peter? Okay, so just ask in my name. You can ask for it. Yeah, please. Okay, so what we wanted to do now is continue with the lecture, okay, after these formalities. And dynamic programming is used a lot in one specific case. I mean, it's anyway used in many different contexts, but one which is extremely widely used is for linear quadratic problems. And that's where it's also making a very convincing case and leading to the most efficient algorithms to solve linear quadratic optimal control problems. And by the way, it's very related to sparse linear algebra, which is a very different perspective, but some people can take that perspective. So today our perspective is dynamic programming, and it's very easy to derive a very efficient algorithm here. So linear quadratic problems. And the problems that I want to state are slightly different than before, in the sense that I will introduce a time-dependent cost now to make it even more general. And there will be a quadratic cost for every time step. I goes from 0 to n minus 1. There will be a terminal cost, which is actually quadratic as well. So there is a matrix Pn multiplied with a vector xn from left and right. And the cost that is here per stage consists of a matrix Qi and Ri, which are both positive definite, but then also some, actually, this restriction, this is not even necessary. We will see what is necessary for this algorithm to work. But usually people choose them to be positive definite, and then there could be some mixing matrix that mixes between controls and states in the cost. So this is the objective that we want to minimize. We will minimize it over all state and control trajectories. I will just denote it by x and u in small letters, but it's the concatenation of all components, just to make it simple. And then our constraints are x0 minus x0 bar being equal 0, okay. Yeah. A matter of taste how I write them. And here I have xk uk minus bk uk equals 0 for k. Oh, sorry, this should be an I, right? I, everything is an I. I goes from 0 to n minus 1. So that's the same setup as before. I make a box around this problem. It's just a special case because now my system is linear and my objective is quadratic. You see the point, yeah? So, what is our dynamic programming recursion? It will just be, I mean, the first thing is what will be Jn of x. The terminal cost to go, I mean, the cost to go at the very end is, of course, the terminal cost, which is this thing here. So it will be x transpose p n x. So it will be a quadratic function. And the good thing about quadratic functions is I can characterize them by a matrix. I need to just store the matrix elements and then I know everything about this quadratic function. So I don't need to go through all states in a state grid or something. I can just know this is the matrix and now I know how to compute that. The next thing is a bit more difficult. So now I have the recursion which says jk of some state x. I drop the index now for simplicity. It's not necessary here. Is given by the minimum of all u in the space of controls of L of x and u plus j k plus 1 of f of x and u. Right? That's the dynamic programming recursion step. And of course, we need to translate that to our specific language here. So the stage, maybe I should have a k here, right? Because this stage cost is now time varying. And I need to represent these cost to go functions. And now there's one thing, the last cost to go is a quadratic function. The stage costs are also quadratic functions. The system dynamics is linear. So if I put the system dynamics linear things into a quadratic function, then I will have a quadratic function again. I add to it a quadratic function, I will have a quadratic function again. And then I minimize over u. And fortunately, that also gives a quadratic function. So if I minimize a quadratic function in 2 variables over one of the 2 variables, then I will get a quadratic. So this thing will again be a quadratic function, and then I can actually represent all cost-to-go functions with quadratics. So the idea, we can actually, jk of x is always represented as something that I call pk x. Yeah, the last one, sorry, already satisfies it, but I will assume that it will be the case for everything, and then I will prove that indeed, if I start with a quadratic here, I will end with a quadratic here, and I will compute it, and then we have an algorithm. The algorithm is, I can summarize it first, and that's, I think, what I want to do. So the theorem 8.1 is already the algorithm, so to say. And it has only one assumption, and it's actually, maybe I should also clarify, I will drop all indices because it will make my life so nasty. But we need to retranslate these indices to make it a real algorithm. Yeah? So maybe I should say, maybe I first write down what we need to do. So what we need to do is we need to minimize this sum. And I assume now that this thing is a quadratic function of this form, and I will drop all indices. So I want to compute this thing, which is x and u transpose, and there's a q, an r, and an s transpose, and an x and a u. And that's this part. And I need to also plug into this part, and that part is actually the matrix P in the middle, and then there's A and B times X and U. So this is one forward step of the system. Then I plug it into the function, and of course I need the same on the transpose side. So I need to have here an A, B transpose and an X, U transpose, right? So that is the sum of these two things. And I need to minimize that thing, and I call this thing J new. Yeah? New is actually the new index, but I want to distinguish it from the old one. So this is this thing, yeah? So this formula. And the theorem says J new equals X transpose P new X. So it's a quadratic. And when can I compute that actually? And there is only one assumption, and this assumption I need to do, I need to state, and so it will be technical, and I will explain why. It's the assumption that the matrix R, BPB, should be positive definite. Then this expression is given by the quadratic. Yeah? So this is a quadratic. And even more, I can specify what this P nu is. P nu will be given by something, and now I should maybe keep in mind, so there is this Q. That's definitely part of it, so it should be a Q. Then there will be something that has to do with this forward matrix. Maybe I first state it and we prove it later. So there will be something that I cannot change either. That's this part. That's due to this product APA. So these are, so to say, the things I cannot change, but then I can change due to the controls and over which I minimize. And therefore there will be some term that I minimize. And there is in the middle the R, B, P, B to the minus 1. That's why I need this thing to be positive definite, so it's also invertible. And then there's a term on the right, which is S plus B transpose P A. And here the same term, transpose S plus B transpose P A. So it's a complicated expression, We will derive it soon, but this is the main result. So if you have this quadratic function, which is the sum of the stage cost and the cost to go then after one time step, if you minimize over u, then this is giving you a new quadratic function, and the metrics you can even compute by this expression. And I hope that you, I mean, of course, I could add all the indices. I would call these things all index k here. Here would be a k plus 1, and then I would actually just get the algorithm, but you will not see the blackboard after all these indices anymore. So I omitted them for a moment. And the proof is relatively straightforward and needs only one interesting result, which we will outsource into a lemma. But the proof goes as follows. So the first thing is that we just note that this thing here is a function of x and u together, right? So what it is, so j nu is actually minimizing over x u transpose and then x u, and there's one matrix only in the middle, and this matrix is the matrix that I get from just bringing this product. That's actually a 4x4 block matrix, and it will have the q and the r and the s transpose blocks, of course, but then there will be something added, which is the thing coming from these blocks, and it will always have a p in the middle. And here, for example, I will have a b, p, b transpose, that's this and that part. Here I will have the same with the a transpose p, a, and here it will be mixed. So here I will have so the s is left multiplied with a u, so there must be a b transpose p, a here, and here the same transpose, so there will be an a transpose p, b, and then it's right from the dimensions. So this is just matrix multiplication. There's no work yet, right? So we just note this thing, and now we simplify that notation by just giving this whole thing a name. So we will just call it minimizing xu transpose xu, and here the matrix in the middle we just call q bar, r bar, and s bar, and s transpose bar. Yeah, so we just summarize this as q bar, this as r bar, to make it even a bit simpler. Please note, yeah, this and this is the transpose of each other, so I call this s bar now. So the bar is just this summary. And then I see, oh wow, I see all these things here, by the way. So if in this new notation, this is just q bar minus s bar transpose r bar to the minus 1 and s bar, right? So it's definitely a useful thing. And that already leads us to the basic step that I need to do now. So we need to show that indeed, and that's a lemma, and I call it the Schur complement lemma, or it's generally called that way. And I will write it down here. So there's a lemma. We call it 8.2, the Schur complement lemma. That's a very simple and nice thing. So it says if r bar, and now I use r bar because it's a general statement, is positive definite, so I make it shorter, yeah, then there is a very simple statement, the minimization over u, when I have this expression of x and u transpose q bar, r bar, s bar transpose. This whole minimization, which is a minimization over the variable u for a specific value x, is given by the expression that I get from x transpose q bar minus, here's the r bar, s bar, and there's one transpose, I think it must be here. And here's a minus 1. So that's the lemma. It just says that if I have a quadratic expression in two variables, and there's one positive definite block in this matrix, then this minimization can be performed and gives me an analytic expression as a function of x, and it turns out to be quadratic in x again. And the proof for this is extremely easy. Maybe I should also say with minimizer, u star as a function of x, given by something that I call just minus r bar to the minus 1 s bar times x. So I even know the optimal value. And the proof of this lemma is very straightforward. What I will do is I will just set the gradient of this function with respect to u to 0. And I will get a term, maybe I should, there is no reason to put it, what would we do actually? We could collect all terms which are depending on u here in this function, and that would be basically u transpose r bar u, and then there is plus 2 times the mixed term, which would be, for example, u transpose this one times s bar here times x, and that same term appears also here in the mixed form, right? So, but it's the same term, and I want to minimize that, minimize with respect to u, and I do it by differentiating it, so I will get the equation, so nabla f equals 0, so that will be just r bar u plus s bar x equals 0, so there is a 2 because this is 2 times, so that is just the derivative of that function with respect to u is that one, and if I invert that, I will get that relation. Once I have this relation, I can plug this minimizer into that formula here, and then I have a complete function of r, and after some cancellations which involve the r bar times r to the bar to the minus 1, I will get actually this expression. So it's relatively straightforward, and the only thing that I needed in order to make sure that this minimization really is unique, I need this to be positive definite. Otherwise there could be no minimizer for that, right? So this whole problem is not well defined if this is not positive definite. I mean, if it's positive, if it's n definite, there would be negative curvature and the minimizer would be infinity, negative, minus infinity. Okay, so this is the little proof. Once I have this result, I can directly use it, use this definition, and I get that formula. And then I'm done. Okay? So with this lemma and this little proof, we have already proven our main theorem. And with this main theorem, we can now write an algorithm. And the algorithm, of course, uses this result. It looks tedious. It will be full of indices, but it's at least an algorithm. So the DP for solving that problem. So for solving which problem? The one that we have here at the top. I should give it a nice index. I give it the same index we have in the script. So that's problem 8.3. So in order to solve that problem 8.3, we go through the following steps. We will just set Pn, we know already, the last cost to go. And then we do the backwards recursion, so we will actually go for k starting at n minus 1 down to 0. So you just go backwards and you define pk to be, and now I need to reintroduce the indices and I just copy this whole thing. So pk is equal to qk plus ak transpose pk plus 1 ak, so this is like what I need to copy here, and then minus, and here I put the r k plus bk transpose pk plus 1 bk to the minus 1, and now I need to have these blocks on the left and on the right, which I need to create a bit of space, sk plus, and here was an a k pk plus 1 bk transpose, and here the same thing transposed, sk plus bk transpose pk ak. Okay, and then you do this recursion, and then afterwards you do a forward recursion. So this is the backward. And now, then, what do you do as the next thing? You make a forward recursion. And the forward recursion will be easy because xk plus 1 is given by ak times xk plus bk times uk, but uk was just given by this formula here. Maybe I write it like that. uk is given by minus rk plus bk transpose pk plus 1 bk to the minus 1 times s bar. S bar was this thing, so I can here have sk plus bk transpose pk plus 1 ak, okay, times xk. Of course, I could also plug this into that system here, and then you get a linear system, by the way, linear time varying system. But yeah, it's a linear map from x that gives you a u. Then you have this forward recursion, and you go 0 to n minus 1, starting with x0 being x0 bar. And at the end, we have solved the problem. So think of what it costs, roughly. I mean, what does it give us as an idea? Of course, we need to invert a matrix here. We need to add matrices. We need to multiply matrices with each other. But it's certainly something that's probably cubic in the state dimension. Not probably, it is. So it's something of the order of nx to the power of 3. And then n times, because you need to go through all the states. The forward recursion is relatively cheap compared to it. But you don't, I mean, you solve this whole problem with a runtime that is linear in n. Yeah? In n and cubic in nx nu. And of course, I mean, there are experts, and one of the experts is a postdoc in my group who make these operations as efficiently as possible. You can implement them so that, yeah, they can be extremely fast and tailored to a specific CPU. And that's something that we use a lot as a sub-problem solver in many algorithms. Okay, so we have now transferred the idea of dynamic programming to linear quadratic problems, and hopefully you agree with me that this is not suffering as much from the curse of not in the same way from the curse of dimensionality as the previous approaches. But of course, it's restricted to linear quadratic problems. You have a remark, or maybe an error? Yes, a question.
So this is an almost unconstrained problem.
Yes, it is unconstrained. I mean, there's like, okay, the system dynamics are the only constraints. Yes.
Would it be possible to introduce other constraints?
Yes and no. So the problem is linear quadratic means linear system, quadratic cost. The constraint makes your cost non-linear or non-quadratic, right? So what people do if they want to just be, so to say, not leave that class, one way would be to just say, okay, I penalize some things strong because I don't want to deviate too much from something. There's also an option to add equality constraints. In some cases, you can incorporate them and still have this same representation. But in order to really deal with inequalities, you in practice, you do other things. And what you do there is you would introduce them into the nonlinear problem. Then this one is the linearization of your nonlinear problem, and then you're back at Newton type optimization. And you use the dynamic programming, or actually we call it Riccati recursion. This is actually the Riccati difference equation. I should give it the name. This is the Riccati difference equation. So it's a very famous equation in control engineering. But from this perspective, it's nothing than dynamic programming applied to linear quadratic problems. And so we call this Riccati recursion, and that's one way to solve basically linear quadratic problems. But linear quadratic problems are subproblems for general nonlinear optimal control problems. And from that perspective, you can deal with non-linear and non-quadratic cost functions. Yeah.
one could just augment them in the system like that, the dynamics?
Yes, so if you want to include equality constraints, like for example, your terminal state should be fixed, yeah, that would be like an easy thing to do. But it will, of course, change the representation of the cost to go. Because your cost to go then needs to not only be a quadratic cost function, because in some dimensions it will be infinity. So let's say if you want to match a terminal state and you go one time step back, most of the states will still be infeasible. Yeah? And only on a, let's say you have a one-dimension control that will allow you actually to move only on a one-dimension manifold on one time step back. And you need to express that, so your cost to go needs to be represented not only by quadratic functions, but in a more complicated way. It needs to have a constraint and a quadratic cost part, but it can still be, so the same idea could be generalized to that case. But it's much down and also to implement it.
Okay.
Yeah.
For the case of static Q's, SNRs, it would still give us
Static what?
Solution,
Static what? Static.
If Q, S, and R are fixed.
Yes. So if all the matrices are fixed, and we will come to that probably next time, then of course things get easier and many things get even nicer and more beautiful.
The question was aiming at, is there like for fixed Q, S, and R, we have a static solution that can be completed offline?
Yes, absolutely. Yeah.
And then just use in the process.
Yes, absolutely. So the interesting thing is, and I will treat that next time, is when they are fixed, these matrices, and the horizon is infinity, then this whole thing results in one single matrix for every time step. And that is then very easy. But I don't want to go to that now. I want to just have one previous remark before. And that is that this linear quadratic problem that we looked at is a bit restrictive. And in many applications, we will not have actually a linear system, but we will have an affine system. So very often, we will have something which is more general. We will have a system that's, for example, given by xk plus 1 is equal to ak xk plus bk uk, but then plus a vector that I could call c, for example, ck. Yeah, so it has some affine term. And also in the cost could be quadratic. And the easy way to remember what to do in this case is the following. I mean, this would be problem 8.6 in the script, but I don't want to write it on the blackboard. So it's actually just something that also has quadratic plus linear. So it could also have a gradient term. Yeah. And the easy way to deal with this issue is that you just write you introduce an augmented form of your system where I just say I have a dummy state that I just set to 1, and that will remain 1 all the time, and then all my system dynamics can be represented with the same notation there. So in that case, you set actually x tilde k to be 1 and xk together, right? And you have an initial condition that just says x tilde bar 0 is defined to be 1 and x0 bar, so the initial value. And your system dynamics will just be given by x tilde being a tilde k times xk tilde plus bk times uk. Now the uk isn't changed. And how do I define these matrices? ak tilde is the old matrix, but it introduces an extra dynamics for my dummy state, which will just be propagated. So it will just remain at 1. Here's my matrix AK, and here's the CK part. So this affine part. And the matrix B is B tilde K is just given by no influence for the first part and BK for the second. So with these system dynamics, I'm back at a homogeneous system, right, without an affine term, without this constant term. And with this, I now have an augmented state, and with this augmented state, I can represent my cost like this. So I will have 1, maybe I write it once in this xk, these two things come together. This is uk, so maybe I have 1 xk uk. I make the division line here, and I will also introduce the division line that we had before. Here's my rk, like before. Here's an s. Now maybe I make 2 more division lines. Yeah. Here's what I had before, sk, qk, sk transpose. But here I introduce some vectors, sk, qk, and here's something I'm not so interested because it's constant. And here is my qk transpose and my sk transpose. So these are vectors and these are the matrices. And you see, because I have the 1, that's, for example, just reading out this first column, it's actually adding a gradient term with respect to the states and with respect to the controls to my cost. So this is a linear quadratic cost now. And for the terminal cost, I will also have actually 1 and xn transpose. And here I will have pn and little p n transpose and some term I'm not so interested in. And with this notation, I can just call this whole thing basically p tilde n, and this whole thing here, sorry, this, what do I have? This one I would call s tilde, and this whole thing I would call q tilde, and the r is identical. So with this substitution, I will be able to recover, and the algebra looks nasty if I would write it down, because now I would have to separate between matrix and vector part and so on. But with this notation, I could just memorize very easily what I need to do. So the trick is just to do a state augmentation where my system propagates a state with value 1 in order to just apply the same formulas without memorizing new ones. You could also derive dp for linear quadratic problems with affine dynamics if you want, but writing down the formulas would be very, very tedious. I don't like to do it. That's why I wrote it down this way. Yeah. Other questions? Yeah, if not, then I want to just say that these linear quadratic problems or linear affine problems, they appear, of course, as subproblems in Newton-type optimization methods, and that's why this special case is actually important. So it's actually what you will use in many implementations. Okay, but next time we will look at infinite horizon problems and also discuss some interesting relations between multipliers and the cost-to-go function. But for now, I think we are closed, and we see you on Wednesday. Thank you.